Curious people, this lecture I want to focus our attention on ideal gas law and ideal gas law processes. Well, ideal gas processes. PV diagrams and how to read them will be main objectives of this class. This is the thermal properties of matter. I'll quickly talk about the matter, but main focus again will be gas in this lecture. In a follow-up lecture, we'll talk about solids a bit more. We all know since the beginning of our career in elementary school that the atomic model of matter, we have atoms and we have solids, liquids, and gases. They could be in three different forms. Solids are more rigid, fixed shape. They have some sort of flexibility. We can model them as springs and atoms tied to each other with those springs at a very basic level. And they have again some flexibility depending on what type of solids we have, but generally their volume is fixed. Liquids are non-rigid, their shape can change, but their volume is also fixed. They're not compressible, and the molecules or atoms are tied to each other as well. For gas, everything is free, shape is free, volume is not fixed. We can change their volume, and particles in a gas, atoms in a gas, moves more freely. So again, we'll focus on a gas. If we put gas in a container, the gas particles will be moving in there freely. Their thermal properties will depend on the average kinetic energy of those particles. Kb here is a constant called Boltzmann constant, and their temperature energy can be their thermal energy can be calculated using that average kinetic energy times the number of particles we have. And this is the equation here. We can also use the relation between thermal energy and the average kinetic energy to find an average velocity of particles in a gas. The position where International Space Station is very high altitude in atmosphere, but still we have some particles, gas particles going around there. A few, but we still have some atmosphere there. Pressure is defined as force divided by the area. Pressure of a gas would be how strong and how often the collisions of these gases to the walls of the container we put them in. Force divided by the area approximation works. Unit of pressure will be Pascal. We won't be really calculating pressure in this context often. It's a simple equation we could, but we will be using the pressure. Its SI unit as Pascal. PA is how we solve it. There might be other forms of pressures, other units. By other forms I mean other units. For example, atmosphere, ATM is used generally for atmospheric pressure. At the sea level, it's 1 atmosphere, and 1 atmosphere is 101,300 Pascal, or 101.3 kilopascal. Americans uses also pounds per square inch, and 1 atmosphere is equal to 14.7 pounds per square inch. And we won't really use this in the science context. This picture here, these two pictures are showing how pressure is directly proportional to force and area. If we apply a force to same area, but we apply larger force on the left, for example, we'll have larger pressure on the left. The pressure inside a barrel is equal to the pressure outside. If we put it outside in the atmospheric, in the atmosphere, we have atmospheric pressure from outside. And bottle's pressure is in equilibrium with it if the bottle is not crashing or blowing out. Now to ideal gas law. Ideal gas law says that the pressure of a gas is directly proportional to its temperature, because if we increase temperature, particles will be moving faster and hit into the wall stronger. Inversely proportional to volume. If we decrease volume, pressure will increase because it will be easier for particles to hit to the walls. So apply more pressure because there will be more collisions. And directly proportional to number of particles. maybe I'll say amount. This is directly proportional to number of particles, and we will express that in moles. 1 mole is defined as 6.02 times 10 to 23 particles. And those particles could be individual atoms or two atoms combined together, depending on what type of gas we have. For example, oxygen 2 has oxygen atoms together, 2 oxygen atoms. So we'll have them together. That's a particle for oxygen. Or if we have a water vapor, we will have oxygen and hydrogen together, right? H2O, we know that. Then it will be our particle. So particle is the smallest particle we have in a gas. Assume it's just one atom. There are monatomic gases, what we call one atom as well. Hydrogen alone could be alone one atom, individual atom. But how many of those particles? That's how we describe 1 mole. If there are 6.02 times 10 to 23 of these particles, that's 1 mole. That's defined to simplify our calculations. And we'll use that for the number of particles. And define the pressure of a gas as pressure times volume is equal to number of particles. This is a regular number. Times Kb Boltzmann constant. That's the constant value. And times T temperature. And I don't really want to focus on this type of equation because we want to use mainly the second version of it. Replacing this guy by N times R. So I can, from here, I can redefine the number of particles in terms of N times Na. Na being this number here. This number is called Avogadro's number. If you guys took chemistry classes in the past, you've heard about it. I listed it here as well. So number of mole times the Avogadro's number is equal to number of particles. We replace that, leaving Kb. These two constants can be combined. Both of them are constant to give us one new constant, R. So we'll define our ideal gas law using R. And that's called gas constant or ideal gas constant. It's a simpler constant than Na and Kb, so I want to stick with that. And it's 8.33 joule per mole times K, Kelvin. And here is the bottom line. Now, why do I trouble you by showing all these? Because you will see these equations and just know that they are equivalent. And we'll use this guy. PV, pressure times volume, is equal to number of moles, small n, times R, gas constant, times T, temperature. This temperature should be in Kelvin in order to agree with our gas constant, which has unit as Kelvin. Kelvin, if you haven't heard of it before, is a unit of temperature, of course, because it's defined in temperature. We can apply the same idea to thermal energy, which also want you folks to use this new version we're going to use. Again, these are more complicated numbers. We combine them, rewrite our equation as 3 over 2 nRT, gas constant, this guy over here, temperature in Kelvin, and number of moles. How many of this much particles in our contained gas? So those are definitions we will need. This page is shortly reiterating the fact that we have to use temperature in Kelvin. So if the temperature is given in different formats, how we convert them is in here. Don't really often use Fahrenheit, although Americans use Fahrenheit exclusively. In the science books, it's generally Celsius or Kelvin. But if we have a question with Fahrenheit, here is how we convert it to Kelvin. And if the question is in Celsius, here's how we convert it to Kelvin. These scales are defined taking the freezing and boiling point of water, our source of life here. So the difference comes from the fact that each defines it differently. For Celsius, water freezes at 0, boils at 100, that's at the sea level. For Fahrenheit, it's 32 and 212. For Kelvin, it's 273 and 373, freezing and boiling. And there's one interesting fact about Kelvin, that the 0 Kelvin is defined as absolute zero. And it's defined at the pressure of any gas. There, two S's, is 0. So when pressure of any gas goes to 0, we have absolute zero. That's 0 Kelvin. And that would be about equal to minus 273 Fahrenheit. Alright, that's how we will do the conversion. The questions might be involving, like this one over here, 2 identical cylinders A and B contain same type of gas, same pressure. Cylinder A has twice as much gas than cylinder B. So PV and RT is our base here. If we have larger N, we'll have larger B. That's the idea there, larger P. But it's telling us to compare the temperatures. Oh, sorry, go back here. No, forget that what I said here. PV and RT is our base. And the question says 2 identical cylinders A and B contain the same type of gas at the same pressure. So pressures are the same. So what I want you folks to do here, write this equation twice. P1 V1 is equal to N R, or N1 R T1. This is constant, doesn't matter. And P2 V2 is equal to N2 R T2. Now if the pressures are the same, right? Pressures are the same. This guy is also same, constant. And 2 identical cylinders means these are also same. How would the temperature change with the number of moles? That's the idea here. So constant, constant, constant. Everybody is constant, only number of moles changes. What you want to do is here is to solve for T1, T2. So if I go from here and see if everything else is kept constant, how T would change with N, I would solve T in terms of N, dividing each side by N, or I'll have T is equal to PV over N times R, right? Same. If N increases, T decreases. I can see that easily. So cylinder A has twice as much, means it has twice larger number of moles, means its temperature will be lower, which is true. A is true. These type of logical questions might arise. And again, basis PV and RT, simple equation. Think about it carefully though. Sometimes it could be 2 things are changing at once. Like in this question. PV and RT. 2 cylinders A, B contain the same type of gas at the same temperature. Now, temperature is fixed. Cylinder A has twice the volume as cylinder B and contains half as many molecules. So, this and this are changing. Okay. This is fixed. And in this case, P is also not fixed, changing. And it's telling us which is true. Compare the pressures. And I have to do this. P is equal to nRT over V, right? How P changes with N and V, that's what I'm looking for. P is directly proportional to N. If N increases, P increases. If I look at P and V, it's inversely proportional to V. V is volume again. If V increases, P decreases. So I can go by logic here. Go by logic. From A to B, let me pick another color here. From cylinder A to cylinder B. A has twice the volume. So this guy has 2V, this guy has V. That means inverse proportionality means PA is PB over 2, right? Half of PB, because inverse proportionality. Larger volume, smaller pressure. But let me write it like this, not like that. PA would be equal to PB over 2. PB is PB, right? That's better. If the volume was only the case here, I would say, okay, PA is half as strong as PB, pressure of B. But it also says A has half as many molecules. So this is for volume comparison. And if I look at the molecules, number of moles comparison, A to B. A has N over 2, B has N. Pressures will be PA is also equal to PB over 2 because pressure is directly proportional to number of moles. Now what did I find? Due to volume, half decrease. Due to less N, half decrease. So when I combine these, I would get the idea that PA is equal to PB over 4. Or PB is equal to 4 times PA, right? And here's the option I have. This is logical approach. And I know some of you folks don't like it. Just do this. P1, V1 equals N1 R T1. This guy is constant. P2 V2 is equal to N2 R T2. Take it as A, take this as B, and put in the values. You say if N1 is N, that's A. If NA is N, let's put it NA. NB is twice that, 2N. And if VA is V, VB is equal to V over 2. Or if VA is 2V, VB is V also would work. A is twice larger than B. I'll just delete that, go that way. It's easier algebraically. Same idea. Input everybody in here and solve. You'll get the same answer. You can also give them values. Since this ratio, it will not matter as long as you stick with the ratio. So if N is 1 mole, right, 2N should be 2 moles, and so on. If V is 1 meter cube, let's say, 2V should be 2 meter cubes. Put them in. Equal things will cancel. Question says T1 is equal to T2, right? Temperatures are the same. Same temperature, so read all the clues. Cancel the same things. When you divide the same thing by same thing, you get 1. And then work on the rest. You'll get the same answer. This one is a simple plug-and-check question, but there are important things to be careful as we solve these questions, so you have to keep it still. What volume is occupied by 1 mole of an ideal gas at a pressure of 1 atmosphere and temperature of 0 centigrade degree? When we see gas, pressure, temperature, something is asked, we'll go for ideal gas law. Important things to be careful about, keeping the SI units. Alright? SI units, Pascal is my pressure. Temperature should be in Kelvin because of the reason that R has Kelvin unit here, and we generally keep Kelvin in scientific calculations. And temperature should be converted to Kelvin then. Volume should be in meter cube. If we need any time to convert it to liters, it's 1 meter cube is equal to 1,000 liters. It's converted here. But after we do the conversions and input everything in, solve for volume. That's what we're going to do, plug and check from here to there. We'll get 0.0224 meter cube. Work out all the conversions, the values given 1 atmosphere. So actually simple, 1.101,300 Pascal. Put them all in, solve for. If you convert this to liter, you'll find 22.4 liter, and this is something this defined as volume of 1 mole of a substance, a gas, and usually used in chemistry often. Another important focus of this lecture is ideal gas processes. They are defined as processes where n, number of mole, is fixed, never changes, and there's a definite value of initial and final values of pressure, temperature, and volume. And in each different process, one of these will be fixed as well, and the others will be changing. But if I look at initial and final values and apply it and take a ratio, P initial, V initial equals N RT initial, P final, V final equals N RT final. Notice N is fixed, so I'm keeping it fixed. We can derive an equation relating final values to initial values. And so for unknowns using this. So keep this in mind. That's one thing. Again, T, temperature should be in Kelvin, pressure should be in Pascal, units should be in SI units. And we can draw a PV diagram, pressure versus volume diagram, to watch the state of a gas, what's happening to it. We can kind of define it like a trajectory of what is happening to a gas. In any state, we can find temperature using the equation above. If I define my pressure, right, volume at that point, maybe another one, pressure, volume, I can see the state of my gas. This could be my initial pressure, this could be my final pressure, and so on, right? And I can follow what's happened to a gas by drawing lines. For example, if I have this PV diagram, I'm going from 1 to here. Let's say this is 1 to 2, and then to 3. I'm going down in this direction. What happens as I do that? As I go along the trajectory, volume stays the same, 1 meter cube, while the pressure decreases from about maybe 7 kilopascal to maybe 3 kilopascal. So this is pressure decreases while volume is the same. This is actually a specific gas process. And if I go from 2 to 3, volume increases. This is my initial, this is my final, while the pressure stays the same. So it gives me a lot of information about what's happening. And there's more to that, and now we'll talk about those. This page has a lot of information. We have 2 gas processes here, specific gas processes. One, constant volume, isochoric, and you can guess from the name. I'm going to keep the volume constant. N was already constant, so what can change here is pressure and temperature. And if I draw a graph, it will look like this. That's the motion diagram, if you like, or the trajectory of the change. We have an initial pressure, we go up, this arrow will show us the direction to go. We have a final pressure, pressure is increasing while volume is fixed. Thus a fixed volume or constant volume, isochoric process. And I can easily maintain that by putting my gas into a fixed volume that doesn't expand much, heat the gas, that will increase the pressure, and of course heating will increase temperature too, right? And I'll have a graph of this sort. Constant pressure is opposite. My volume will be changing, increasing in this case, while pressure is constant. I can easily maintain that if I put something outside in the atmosphere, there's going to be a force by the atmosphere, so there will be an atmospheric pressure as external pressure. And if the piston here can move up and down easily, gas pressure will always be equal to external pressure or atmospheric pressure. So pressure can be kept constant while the volume changes. There's one important information here. Gas is doing a work here, pushing the piston up. and that work done by the gas can be found using this area. So area under is the work done by the gas. In the simple case, we can find it using the sides, right? It will be this times that, and that distance is change in V final minus V initial. So we can even derive an equation for it. But it's not always a simple case like this. For example, here if I see there is no area under the curve, so work done by the gas is 0. Gas is not pushing or pulling or anything, so it's not doing any work. We can also relate what's happening to temperatures by looking at the change in thermal energy being equal to heat given into system. I'm giving a heat into system here, minus the work done by the gas. Simple equation. This is actually called the first law of thermodynamics. So I can find the work here. If somehow I know how much heat I give to the system, take that away from work of gas, I can find how much thermal energy changed. This being our thermal energy equation, change in thermal energy can be found using change in temperature as well. And we'll walk through those via some examples. Third process is called isothermal process. Temperature is constant. And we can maintain it by isolating a system and keeping it at the same temperature and then pushing on change in the volume of a gas, for example. Constant temperature. In this case, since the volume is decreasing, pressure will increase. So we'll get, if we draw a pressure versus volume graph, we'll get a graph of this sort. It won't be a straight line here because pressure is inversely proportional to volume. We'll have a curved line. Still, the area under the curve is equal to work. And if the volume is decreasing, the gas will do a negative work. Here you see volume initial is larger than final, so gas is doing a negative work. And it's area under the curve, but it's not very easy to calculate in this case. So we won't be going into trouble of calculating this, which is more complicated than what we want to cover here. But we can do comparisons. For example, if I have many different temperatures and each has isothermal process, as I move in this direction, temperature will increase, as you see in this plots here. These are called isotherms. I can also check which one gas is doing more work by looking at their areas. This area here, let's call this work 1, is larger than this other area, the yellow one. Let me show it like this. Sorry, smaller than this area here. Let's call the yellow one is work 2. So work 2 is larger than work 1. Assume each of them are going in this direction. Work will be positive. Oops, let me choose another color here. Because V initial will be that, volume initial, and volume final will be that. Final is larger, we'll have a positive work. The other direction is also possible. Let's say this guy is in this direction and volume is decreasing, work of this dude will be negative. Let's call it work 3, smaller than 0. This guy is bigger than 0, also bigger than work 1. Work 1 is bigger than 0, work 2 is smaller than 0. Then gases do negative work. This actually means somebody else is doing work on the gas. Equation still holds. Delta E thermal equals Q minus work. Since temperature is constant here, isothermal, this guy will be 0. Q will be equal to work because that guy is 0. Work of gas. And the last process is adiabatic process. The idea for adiabatic process is that it happens really quickly, so the gas doesn't have time to take or give any heat to outside. So heat given or taken is zero. Q is zero here. And either it could be compression or expansion, temperature changes. If we have adiabatic expansion, temperature lowers. And if we have adiabatic compression, temperature rises. For example, this from history, this picture here is showing surface temperature of North America in Fahrenheit in winter, and we see that the temperature increases this way. What happened here, actually, there was a wind called Chinook wind blowing from Rocky Mountains down, and as it blows, air compressed adiabatically. Since no heat in and out, there was no time for taking heat from outside or giving heat to outside. The air heat, the temperature increased, and we saw an unusually hot days in the winter. This explains the details of it. Applied to this equation here. Expanding gas would go in this direction here. Again, two directions are possible, right? It can go in this direction. My process might be going in this direction where volume is increasing. This is pressure, this is volume. And then work will be positive. If the work is positive, Q is 0, we will find the E thermal here is smaller than 0. It should be smaller than 0. Because Q minus W, Q minus work is E thermal. That means delta E thermal is smaller than 0. Delta E thermal is final minus initial, right? Thermal final minus delta E thermal initial. So final, if this is smaller than 0, that means final is smaller than initial. Temperature drops. This case is adiabatic compression case. Opposite happens. So we have increase in temperature. Alright, some examples here. Again, idea. N is always fixed, constant. Alright, and other than that, some other values will be fixed depending on the process. So this example is about isochoric, fixed volume or constant volume process. If I draw a graph, this also could have two directions. Volume is constant, pressure is increasing up. It could also have a case it's decreasing. Constant volume. Change in pressure. The question says the temperature of a rigid sealed container of a gas, rigid sealed, so rigid tells us that the volume is constant. Increases from 100 centigrade to 200 centigrade. So this is T initial. This is T final. The gas pressure increases by a factor of what? I can start from here and work through it. This guy is fixed. This guy is fixed, right? Or I can start from here. These guys will cancel because they are also fixed. If I set this to V and V, they will cancel. Either way, it will give me this information. P initial over T initial equals P final over T final. I know T initial, T final. I can compare P final to P initial. Just solve for P final. Multiply each side by T final. You'll say this. P final is equal to P initial times T final over T initial. How many times P initial will come out of there? One important thing is that you guys have to convert to Kelvin, Celsius to Kelvin. Always use Kelvin. So here ratio will change. You'll add 273 to convert to Kelvin. Please go ahead and do this, and you should find that value there.